Imagine that we consider a function in the xy plane given by the equation y equals g of x. And that we only consider this function on a fixed interval from x equals a to x equals b. And that inside of this interval we take an arbitrary value for x, and we consider the function at that point. So the y value, of course, is g at x, so g of x. And let's consider the tangent lines of the function at this point. Let's now add to x a small change in x. For the sake of the picture, we're going to assume that the change in x is positive, but it could very well be negative. So x plus delta x. So here, because x is the independent variable, then delta x will equal dx. And now we want to compare the respective vertical change in the tangent line and in the function as we go from x to x plus delta x. So first, let us consider the vertical change along the tangent line. So we go from here to here. This, of course, is given by the differential dy. Now the y value on the function here is this point, and of course the y value at x plus delta x is g at this point, g of x plus delta x. And now we have the corresponding change, the exact change in the function as we go from x to x plus delta x. And we denote this by delta y. Now it's clear from the picture that dy, the differential, the change along the tangent line, and delta y, the exact change along the function for the same change in x, these two are obviously different. What is interesting, of course, is that the smaller delta x is, the closer the second point is to the first point, and so the closer the change along the tangent line is to the exact change in the function. So dy, the differential, the vertical change along the tangent line, can serve as an approximation to delta y, the exact change in the function. What we are interested in this video is measuring how good of an approximation delta y is, or sorry, dy is to delta y, of course, as a function of the change in x, delta x. So first, how do we calculate both changes? Well, delta y is obvious. The y value at x plus delta x, g of x plus delta x, minus the y value at the initial point, g of x. The differential dy being the change along the tangent line, it being a vertical change, this is of course given by the slope of the tangent line times the change in x. Well, the slope of the tangent line, of course, is the derivative of g at x times the change in x, which usually, in the case of a differential, we write as dx. But again, since x is the independent variable, delta x and dx are the same. But of course, that is not the case for dy and delta y. Those are approximations of one another. So, again, we know that dy serves as an approximation to the exact change along the function, but our goal again is to evaluate how good of an approximation dy is to delta y. And for this we have to make one key assumption. It may not be clear at first why we make this assumption, but it will become obvious as we go along the argument. And the assumption we make is that not only do we assume that the second derivative of g exists, but that it is also continuous on the interval from a to b. Now, since the second derivative is continuous on this interval, so will its absolute value, and therefore, by the extreme value theorem, the absolute value of the second derivative will achieve a maximum value on the interval from a to b, which means it will be bounded absolutely by a fixed constant, say m. So where m is a fixed constant, and this for any point inside of a, b. So again, this is a consequence of the extreme value theorem. Because g double prime is assumed to be continuous on AB, so is its absolute value. Therefore, it must be attaining inside the interval an absolute value, call this value m. So the second derivative at any point inside of AB in absolute value is at most this fixed number m. That is the one assumption we make. Now we are good to go. So again, we care about the error of our approximation. The error, of course, is the exact value, so delta y, the exact change in the function, minus the approximate value, dy, the change along its tangent line. And we don't care so much for the error, but for the size of the error. So what we care about is estimating the error in absolute value. How big is the error? Well, delta y is g of x plus delta x minus g of x. Minus dy, which is of course g prime of x times dx. And I will now replace dx by delta x. The question now is, well, what do we do with this? Well, we have g at x plus delta x minus g at x. We can apply on this the mean value theorem of differentiation, right? A change in a function from one point to another can be given by the slope of the function at some point, say x1 between these 2 points, times the change along the x-axis. So this minus this gives us delta x. And x1 is some point between x and x plus delta x. So say x1 is here. But x1 could be anywhere between the original point and the new point. Again, this is a consequence of the mean value theorem of differentiation. And we have the second term now from the differential. Notice now that we can factor a common multiple of delta x. Since delta x could be negative, although in the argument now we are assuming delta x is positive, but the argument works just the same if delta x was negative, and because of that possibility we will factor delta x and leave it in the absolute value. And now this is interesting, right? We initially had a difference of g at 2 distinct points. We now have a difference of g prime at 2 distinct points. And because we assume that the second derivative existed, we can apply for a second time the mean value theorem, not on g, but now on g prime. The change in g prime at 2 distinct x values will be equal to the second derivative, right, the derivative of the function g prime, which is the second derivative, at some point x2, between x and x1, so x2 will be somewhere inside this shorter interval, say here, times the change in x, so x1 minus x. Times delta x in absolute value. This, of course, equals the second derivative of g at x2 in absolute value times the absolute value of x1 minus x times the absolute value of delta x. And now things become interesting, right? x2 is somewhere in the interval from a to b, therefore in absolute value, the second derivative at x2 is at most m. So we have an upper bound for this term. Then how big can x1 minus x be? Well, if you notice, x1 is inside of the interval from x to x plus delta x. Therefore, x1 minus x2 is at most the length of the full interval, which of course is delta x. So this term is also at most delta x in absolute value times delta x in absolute value. So we now have a rather elegant upper bound for the size of the error. The error in absolute value between the exact change in the function delta y and the change along its tangent line dy will be at most a constant times the change in x squared. And now let's state our conclusion. What do we have? We have initially the exact change along the function. Delta y is g of x plus delta x minus g of x. Then we have the differential dy, which is the change along the tangent line given by the slope of the function at x times dx. Again, recall that dx equals delta x, since x is the independent variable. Then the error, of course, is the difference between the exact change and the approximation, the differential. And in absolute value, the error is at most some constant times the size of delta x squared, where m was the absolute value attained by the second derivative on the interval. So we can write this nicely as where m, again because we assume the second derivative of g was continuous on the interval from a to b, so m is the maximum over the interval from a to b of the absolute value of the second derivative of g. And this is interesting because it tells you that the error is very small, right? If delta x is small, this is the main comment. If delta x is small, and again, why do I say delta x is small? Well, we know from the picture, right? It is obvious that if delta x was very large, then the differential would be a very poor approximation to the exact change along the function, right? The bigger delta x is, the worse the approximation gets. But from the picture again, intuitively, the smaller delta x is, the closer dy is to delta y. So we only have a good approximation from the differential if delta x is small. And I can even put this in absolute value, right? The size of the change in x is small. And by small I mean less than 1. Then the size of delta x squared is even smaller. And I'll even use the word much. And again, by small, what I mean is in absolute value delta x is much less than 1. So as an example, say the size of delta x was 1 over 1,000, so 1 over 10 cubed. Then, what is the size of delta x squared? Well, if you square 1,000, you have 1,000,000, so 1 over 10 to the 6. So you can see, suppose your delta x is on the order of 1 over 1,000, then the approximation dy will be a constant, right, the slope of g at x, times delta x. So it'll be some constant times 1 over 1,000, but then the error will be at most some constant times the size of delta x squared times 1 over 1,000,000. So while the approximation is on the order of 1 over 1,000, the error is on the order of 1 over 1,000,000. So relative to the size of the approximation, the error is much, much smaller, an order of magnitude smaller. But again, this only makes sense if delta x is very small. We can see this algebraically, and we can see this geometrically. So of course the constant m depends on the maximum value of the absolute value of the second derivative on the interval from a to b. But hopefully this gives you a more explicit reasoning as to how good is the approximation of the exact change in the function from the differential of the change along its tangent line. And when delta x is small, delta x squared is much smaller, and so the error of the approximation will be an order of magnitude smaller than the size of the approximation. So for small changes in delta x, dy is a very good approximation to delta y. And that's it.